Yes, class. Good evening. Audible to all of you?
Yes, ma'am.
So, who all are there right now? Khalid, Salman, Samaira, Zaid. All right. So, in the last class, we had started with this lesson, and we had actually covered a major portion of bar magnet. This is a very short topic. If most probably it's possible that we can end this lesson today only, because we have the 2-hour class. We didn't do any numerical on this, no? We had done this question derivation and this. Let's do 1 or 2 numericals, then we can move on to earth magnetism. That's the question. Earth magnetism is included in your syllabus, no, right now, in your class 12.
No, ma'am.
Earth magnetism has also been deleted.
Yes.
All right, then it's very good. Bohr magnetron, that small topic is that we'll be able to end this class fast. Let me give you a few questions on this first. So I did send all of your marks on WhatsApp group. Let me just show you your papers. Z is here. This is a mistake that Z made. Direction. Not the specific, just the specification of direction. Your Z, your paper was fine. The rest of it was fine. Let's same thing, direction, Khalid, direction. In the first question, it was specifically asked even to write the magnitude and the direction. So direction only. I think most of you have committed errors of direction. Maimuna didn't join, no? Right now? She didn't give the test also. Hania gave the test. Hania. Again, see, you have calculated the magnetic field for a single loop only. So don't calculate it for a single loop. See, you have to take it for both the loops and then take the direction. Otherwise, you'll get the half score only the way it's written here. And in the second question, just the error of calculation. Rest of the things you did it fine. Mainly, Hania, what happened with you was the formula writing. You eliminated the angle that is included. So all your answer came wrong. And in the last question, I think same thing occurred. Your calculation mistake. So I think you just need practice because the basic things that you have written was fine. Salman, direction only. Anyone who is there in this batch? Samaira. Samaira gave the test.
Yes, ma'am.
What happened with Samaira was, yes, same thing that happened with Anya. Both of you got the same answer, 30 into 10 to the power minus 4. I don't know how you both got it. So these are the errors. If you want me to discuss any of the solutions, let me know. Last question, you did it fine, Samaira. It's just that direction and that wasn't written. The SI unit and the magnitude was it. Just the first and second question, there was some error. So I think all of you are doing well. Even students who have scored lesser score, no, we are on maths. So students who have scored lesser score also, you people have the concepts well. It's just that you have to do practice. Like other students, Zaid, Salman, Khalid, and also those who have scored a good score, their concepts are same. It's just that you have to increase your practice because there will be a shortage of time and you don't know what will happen whenever you are giving your board examination. For example, I'll tell you my experience. When I was appearing for my 12th board examination, the physics paper that came in this Delhi zone, because in India we have different zones for every paper. So here the paper that I got for Delhi's paper, the paper was very lengthy, and I'd never seen such a paper. So the students who had the speed very slow and their accuracy was slow, they weren't able to score. I think maximum they were able to score till 85 only on 100. And obviously you people know the values of percentages. You have to have a good high score. Unless and until you get 92, 93, like these scores, minimum in each of your subjects, and only you'll be able to achieve a good percentage. That sounds like 95%, 94% and all. So anything can happen when you are solving the test. It may seem like the papers which I was practicing during my time. So it's different thing that the syllabus was different, pattern was different and everything. But even from that also, if you leave all those things apart, I had never appeared for such a lengthy paper. But the physics paper turned out to be very lengthy for that year. So the paper can be lengthy. Okay, someone has answered. Z. Same thing, Zed. What you did in case of your paper, same thing, you're doing it right now. Units, you are writing it correctly. Magnitude, you are writing correctly. Direction, don't forget to write the direction. Whenever it's a vector quantity, by yourself only write the direction. And if you need any help, any one of you, it's not specifically for someone, if any one of you need help in any of the topics, because we have many batches in the previous, like Zed also joined. So Zed, you saw that day we were on such a previous topic that you had already covered. So likewise, if you people miss any topic and you want, or you have even attended and you're not confident about it, so you can let me know. We have special teachers also who focus on certain areas. So whatever is the issue, you just tell me. So I think, Hanya, as you've already told me that it was some lack of practice that was occurring. So I hope you're practicing now, Hanya. And what about you, Samaira?
Yes, ma'am.
Practicing? Just practice more. See, your concepts are fine because you just remember the formula. And just to improve the accuracy, just keep on practicing. Try to do the assignments if you do not get questions, or if you need more questions, more easy level questions or more difficult questions, let me know. I'll make the assignment according to that only. That direction. Yes, right. Khalid is right. Both of you, Zaid and Khalid, your answer is right. Magnitude will be 7.2 into 10 to the power minus 4 only. Let me solve it now. So magnetized needle of magnetic moment. So capital M is written as 4.8 into 10 to the power minus 2 joules per Tesla. Is placed at 30 degree with the okay, direction has already been specified. Fine. Then both of you, your answers are sufficient. No need to mention the direction because it has been written that it is placed at 30 degree with the direction of uniform magnetic. So theta is what? 30 degrees. So this is the easiest question possible. Magnetic field. Okay, last year those questions, those sections were deleted where it had the differentiation of paramagnetic, diamagnetic, and ferromagnetic. Is it included this year? Anyone has any idea? Zaid?
Ma'am, I think different like derivation is not.
No, not the derivation. There's a section in your syllabus that was deleted last year where there are theoretical points on difference
Yeah,
between
it
diamagnetic
is there. Yeah,
It is there, no? It is there. Because last year, fine. So magnetic field is given 3 into 10 to the power minus 2 Tesla. Torque. So torque was M cross P. That becomes MB sine theta. Now let's just put in the values. So this becomes 4.8 into 10 to the power minus 2. Magnetic field is 3 into 10 to the power minus 2. And then sine 30 degree. So yes, when you will solve this, you will get the answer as what they both are getting. 7.2 into 10 to the power minus 4. And since it's torque, SI unit will be Newton meter. Let's do one more question on this. Just one more question. First, note down the solution. We'll do one more question. Yes, angstrom into meters. Angstrom, you have to find out current.
I'm sorry.
Amperes. Yes, right. Magnitude is right.
Ma'am, magnetic moment should we get from like intensity of magnetization, that topic?
Magnetic moment, the formula of magnetic moment, simply the formula of magnetic moment. See, current you have already calculated from the first part. Zed, I think your second answer is not right. Just check your second answer. Some error in the powers of 10, I think you must have done. That's why you're getting this, because magnitude is somewhat right. Khalid, all the three answers are right. Last, I think let's take last 2 minutes, then we'll discuss it. All of you try. Rest of you also try. Samaira, Salman. Yes, Salman. All the three are correct. Yes, Zed. Third one is correct. Zed, did you see the calculations for the second part? Just check one second one, then we'll discuss it. Okay, let's discuss it then. It says an electron moves around the nucleus in a hydrogen atom of radius 0.51 angstrom with a velocity of 2 into 10 to the power 6 meter per second. You have to find out equivalent current due to orbital motion of electron. Equivalent current means current. So current is basically charge divided by time, or time period also. You can write it as distance, that is 2 pi r divided by velocity. This formula we've already done it. See, this is the nucleus. No, this is the distance. So electronic charge is 1.6 into 10 to the power minus 19. Velocity was what? 2 something, no? 2 into 10 to the power 6. Velocity is 2 into 10 to the power 6. 2 pi is 3.14. Radius is given as 0.51 angstrom. Samara, how do we convert angstrom into meters? Yes, Samara, how do we convert angstrom into meters? Anyone else? How do we convert angstrom into meters? How should I write 0.51? Yes, Ed.
Ma'am, 10 raised power minus 6.
Yes, right. 10 into 10 to the power minus 10. 10 raised to the power minus 10. So when you solve this, you will get the answer as 10 to the power minus 4 ampere. That's the current. Now, second part says magnetic field produced at the center of nucleus. So, center of nucleus means what? At the center of nucleus, it's basically like the center question that we did. Remember, we had derived a derivation on the magnetic field at the center of a circle. So, magnetic field's formula that we'll be using, this will be mu naught I divided by 2r. That's the magnetic field at the center of a circle. So mu naught will be 4 pi into 10 to the power minus 7. Current from the first part, 10 to the power minus 4, 2 into radius, 0.51 into 10 to the power minus 10. Once you solve this, you will get it as 1.23 Tesla. Zed, where was the mistake? Now are you able to identify it? Calculation error.
Ma'am, I got like 1256.
Remember, see, the magnitude is same something. That's what I'm saying. I think in the powers of 10 there must be an error. That's why this 1.256 you should get.
Yes.
Just see the calculation. I think if you have written all these things, what I've written on the board.
Ma'am, I wrote B equal to nu naught Ni. That formula I used.
Okay, mu naught Ni. Then obviously with pi it will be a little different. Fine, that's also fine, mu naught Ni. But for the circle, we have exact this formula. So I think that's where the variation came. That's why the powers of 10 and everything were coming huge. Last part is magnetic moment associated with the electron. Salman, what's the formula of magnetic moment? You there, Salman? Hania, formula of magnetic moment? Magnetic moment is current multiplied by area. So magnetic moment, this is current multiplied by area. That's why we got the equation. No, remember for torque we did NAIB because this is M cross B. That's from where we got all these things. So current from the first part, it is 10 to the power minus 4. Area will be, you can write it as 2. Okay, it's better if we use this. See, if you write all these things, no, either you can use 10 to the power minus 4 and use pi r square for the area of the circle, or you can do one thing also. You can put current's value as this, then pi r square. So pi and 1 r can get cancelled. Otherwise, same thing. By both the methods, you'll get the same answer. So this is 10 to the power minus 4 pi 3.14 r square, means 0.51 into 10 to the power 10 square. When you solve this, you will get the answer as 8.16 into 10 to the power minus 25 ampere meter square. All right, note it down, those who haven't done it. Now, some terms used to describe magnetism. So, as this topic, one topic is left for the classification of material or for the classification of magnets. You first have to identify certain terms, and these terms can also come in your exam, like define the terms magnetizing field, magnetic induction, and all these terms. So, first one is magnetizing field. See, when a magnetic material is placed in a magnetic field, a magnetism is induced in it. This we have already seen in your chapter number 4, where we had dealt with magnetic effects of electric current. When the magnetic field exists in vacuum, see, when the magnetic field exists in vacuum, and then it induces magnetism. At this time, we call it as a magnetizing field. For example, you can take the example of a toroidal solenoid carrying current I and is placed in vacuum. So what happens? Number of turns that we take. If solenoid has, let's say, n number of turns, so magnetic field is written what as how? Mu naught Ni, the formula that you were using there. So this field that we get now, this is known as the magnetizing field because it is caused by the so-called free current in the solenoid. If this is kept in vacuum, if this is kept in vacuum, then only, then we call this magnetic field as a magnetizing field. So magnetizing field and magnetic field both have just a slight difference in between them. Otherwise, just of the properties, unit, and everything will be the same. Now, the second property that you have is magnetic induction. So induction we will be seeing in detail. One induction we have already studied in chapter number 1. Remember methods of transferring, methods of charging, how to send the charges. So conduction, charging by conduction, charging by friction, charging by induction. There we had seen induction. Second induction is over here, magnetic induction. Third will be the whole complete chapter that we'll start from third. That is your electromagnetic induction. So here we are just focusing on magnetic induction, the magnetism part. See what happens when a magnetic field material, or this is kept in magnetizing field. Let's say this is some circular ring is given, and we have wrapped it with a help of wire. So what will happen? Ultimately, this material with which we have wrapped it with the wire will also develop magnetic field. So total magnetic field inside this magnetic material. This is what? This is sum of all the fields that it is containing. So that's why we call it as magnetic induction. Or magnetic induction, you can remember it simply. Magnetic field lines you are aware of. So whatever magnetic field lines are crossing per unit area, normally you call it as magnetic induction. That's a better definition to remember. But just for understanding, magnetic induction. Induction, this term means to induce. Induce something. So that's why we use this term magnetic induction. This means to induce. Or you can simply write this magnetic induction as number of magnetic fields not magnetic field, magnetic field lines of force crossing unit area normally. This is known as magnetic induction. And SI unit is Tesla. You can use the SI unit for both of these as Tesla for both of these. All right. Third term that let's discuss is the magnetic field intensity. This is magnetic field. Magnetic field intensity. So magnetic field intensity, this is represented by this vector H. So ability of magnetizing field to magnetize any material medium. This is represented through this H. We call it as magnetic field intensity or just simply magnetic intensity. So how can we write its magnitude? Simply it's defined as number of ampere turns, means number of turns that are flowing multiplied by the current that it is having. This is its formula. Basically, this is there to produce the magnetizing field. Also, you can write B is equal to mu naught Ni. So from here, you can have the value of N. What will be the value of N? N will be B divided by mu naught I. Let's keep it in this formula of magnetic field intensity. If you keep the value of N from here, H will be equal to B by mu naught I multiplied by I will get cancelled. H will be equal to B divided by mu naught. And mu naught is your permeability. Regarding the dimensions also, you can remember it's L minus 1 into ampere. That's the dimension for it. And from by looking at the dimension, you can easily conclude the SI unit. It will be the same ampere per meter. For current, it's ampere. See, SI unit will be simply current divided by length. This will be ampere meter. Dimension, you can calculate it from here using this. Now, this was magnetic field intensity. One term you have it as intensity of magnetization. One term that is present is intensity of magnetization. Intensity of magnetization. See, magnetic moment per unit volume is known as magnetization. So when you have to write the term magnetization, this magnetization simply means magnetic moment per unit volume. V is the volume, M is the magnetic moment. V is the volume. So intensity of magnetization, it is basically the pole strength. Poles we have done, north pole is there, south pole is there. So the strength of these poles that is developed for a unit area of cross section. We call it as the intensity of magnetization. Let me write down the definition of it. It can be confusing with magnetic intensity. So it is defined as the pole strength developed per unit cross-sectional area of a material. And one important formula that you have to keep in mind is a relation that is connecting magnetic field or magnetic induction. You can use both these terms together. Slight difference is there, which I've already told you. So magnetic field is written as mu naught H plus M. Means intensity of magnetization plus magnetic field intensity. This is a relation. First, note down these 4 points. Any doubts in these terms, ask me. Then there are few terms left. Okay, Salman, fine. Magnetic field intensity. Okay, this one, magnetic field intensity. See, the ability of magnetizing field to magnetize a material medium. This is known as magnetic field intensity. I'll give you an example. You must have done electric field. Electric field is different. Electric field intensity was different. Similarly, magnetic field is different. The intensity with which the magnetic field is able to magnetize a material, that intensity we call it as the magnetic field intensity. So magnetic field intensity, or you can simply say magnetic intensity. So how can you define it? You can define it as the number of ampere turns, that is Ni, N into I, number of turns into current, flowing around the length of the solenoid required to produce whatever is the given magnetizing field. In simpler terms, you can just understand that magnetic field exists, and the ability of the magnetic field to magnetize a material. There should be a specific intensity, then only a magnetic field will be able to magnetize a material. That intensity of magnetic field, this is known as magnetizing field intensity, magnetic field intensity, or simply magnetic intensity. Is this clear, Samaira, or any other doubt?
Yes, ma'am. Clear.
I've already told you that there are few terms left that we'll discuss once you people write it. More terms that other than magnetic susceptibility.
Yes.
Now the fifth term is magnetic permeability. Now, permeability is basically the measure of extent to which a material can be magnetized. It's the extent to which a permanent magnetic field can be applied, or how the magnetic field can get penetrated into the substance or be permeated by a magnetic field. That extent we call it as the magnetic permeability. So you can also define it as the ratio of magnetic induction that you have studied, which was B, and the ratio of magnetic intensity, H. This also you can write. So SI unit of permeability we already know. It's the same permeability, mu naught, whose value is 4 pi into 10 to the power minus 7. Same. Unit will be Tesla meter per ampere. And if you wish to know the dimensions, dimensions will be ml t to the power minus 2, a to the power minus 2 also, yes. This will be the SI unit. Now, this was magnetic permeability. You have one more relatable term to it, which is known as relative permeability. This term is known as relative permeability. So, relative permeability is basically in comparison with other materials, like permeability of various magnetic substances can be compared with another in terms of relative permeability. So, like if one medium is air, other medium can be glass, other medium can be water. So by changing different mediums, you have different media, you have different values of permeability. So that allowance or that extent in different mediums, that is governed by relative permeability. And this relation we have already done when we were discussing epsilon naught also. Remember when we did epsilon naught, all these three. Similarly, relative permeability will be permeability divided by permeability in free space, similar to whatever you studied in electrostatics. Then we have the term known as magnetic susceptibility, which you were reminding there. So this is magnetic susceptibility. Now, susceptibility, you can easily figure it out from the term ability. Magnetic susceptibility measures the ability of a substance to take up magnetization, how it gets magnetized. All these terms have slight difference. In actuality, we use the term synonymously. But like magnetic permeability, relative permeability, they have a difference that we know. So that's why we are studying it, as when we will classify the materials, classification of magnetic materials will involve all these terms. So magnetic susceptibility is what you can, yes, one thing that I told you, that it's the ability of a substance to take up magnetization whenever it is kept in magnetic field. Apart from this, magnetic, let me write down this definition also. It measures the ability, this magnetic susceptibility measures the ability of a substance to take up magnetization in magnetic field. Now the formula for magnetic susceptibility, this is represented through the symbol chi. The symbol is called as chi. You must have used this in your chemistry, mainly when you have those partial pressures and all, mole fractions, we use the symbol chi. So there you must have seen it. So we just put an M to distinguish it from others. It's actually the ratio of intensity of magnetization. Remember intensity of magnetization to the magnetic field intensity H. So this is the formula. You don't get questions to solve it, but these come in your theoretical aspects. And from your theoretical aspects, you are asked to write all these. So hardly I've seen numericals coming from it. One last is the relation between magnetic permeability and magnetic susceptibility. See, magnetic field was what? Mu naught H plus M. Right now we had done this. But we also know that magnetic field, this B, is also written as mu into H. This is mu naught. This is mu. Remember, mu is equal to B divided by H. We have derived. From here, we can write it as this way. So mu H will be equal to mu naught H plus M. Fine. So if we divide all the terms by capital H, divide by H. See here only mu will be left. From here it will be 1 plus M divided by H. Can you notice one thing? M divided by H, we have just done it. That was magnetic susceptibility. So this derivation can come. This is a very short derivation and it comes in the 2 markers. So this you can learn the derivation. Above from all these things, this can be asked for your question. Fine, so note down the rest of the 4 points. These 8 points are enough. So now the last portion of this lesson is classification of magnetic materials. So either a very short note for 2 marker can come to write on any of the materials, like write a very short note on ferromagnetic materials and all. Otherwise, a difference come, usually difference come, differentiate between diamagnetism, paramagnetism, ferromagnetism on the basis of uniform magnetic field like this. So I'll send you all a table on WhatsApp, most probably by tomorrow or today only I'll send you all. From there you can learn all the minute details, but let's just discuss first the diamagnetic substances. Diamagnetic substances. So these are those substances that develop feeble magnetization. Feeble magnetization means very, very weak magnetization, light magnetization. In which? In opposite direction. Opposite direction to what? To which thing are we taking the magnetization in opposite direction? To the magnetic field. To magnetic field. So they developed the magnetization in opposite direction, and the magnitude is also very feeble. It's very feeble. So, and they are repelled weakly by the magnets. Feeble word is used in, I think, NCERT. It's used. Your feeble term is used, so it's better if you use this term. But feeble means weak. So these substances are feebly repelled by magnets. Means weakly repelled by magnets. Feebly repelled by magnets. And one more thing, one last point that you have to keep in mind is that they move from the stronger parts of the magnetic field to the weaker parts. If I say the magnetic field is strong over here, and at this location it is weak, so they tend to move from stronger part to the weaker part. I'll write down this as well. Tend to move from stronger to weaker parts of a magnetic field. So different examples are there. Even you have this in your chemistry. I think, is it included now in chemistry in solid state? I think it was included in solid state.
Ma'am, कुछ please them out.
So any material, most of the metals and our conductors are the diamagnetic substances. Like you can take the example of copper, you can take the example of lead, you can take the example of gold, and all these metals. Oh, this is silver, so you can take the example of all these materials. These are the diamagnetic substances. Example 1 or 2, if you remember, that's enough. You won't be getting questions directly on example. Second substance that we get. Second substance is your paramagnetic substance. It's paramagnetic substance. And regarding this topic, no classification of material. Questions come in exam, not only in your entrances, in your board exams also questions come. Water and salt. Yes, water, salt, these will be paramagnetic substances. Water will be diamagnetic, sir. Salt is paramagnetic. Salt, your NaCl, no? Or even copper chloride, sodium chloride, all these are paramagnetic. Water will come in diamagnetic. Paramagnetic substances. So this topic you just have to learn everything. By learning, you will get score in this topic. So these are substances that develop, again, they also develop feeble magnetization. Feeble magnetization. Permeability and susceptibility, that's what I was telling you, Zaid. First, let us just discuss the brief points, the major points. And as I've told you, I'll give you the table also where everything is written. Everything will be included. Permeability also we have to consider, susceptibility also we have to consider, movement in external magnetization, movement without external magnetization, and everything. So that, as I was saying, as you have to learn that table. So that's why I did these topics separately, permeability, susceptibility. So just at the end, you have to learn it. So that's why the major points, no, which are your physics oriented point. That's what we are discussing right now. Few major points. So this also develops feeble magnetization. But the difference occurs in the same direction. In the same direction to magnetic field. This is one of the differences that arise. And feebly means weakly attracted by magnets. They are weakly attracted by magnets. And regarding those portions, they tend to move from weaker to stronger parts. That's the difference that arises. They tend to move from weaker to stronger parts. Tend to move from weaker to stronger parts. So these examples there's already mentioned sodium chloride, copper chloride. These examples, what else? Normal aluminium, manganese, chromium, all these materials, these will come under this one. Aluminium, yes, aluminium, sodium, yes, sodium will also be there. Sodium is there, as I've already included in sodium chloride. So sodium is there, aluminium is there, yes, right. Now, the third and the last substance that we'll discuss is your last one is your ferromagnetic substances. So the third substance group of substances that you have is ferromagnetic. These are the ferromagnetic substances. Now slight differentiation will arise. Feeble magnetization, they develop strong magnetization. They develop strong magnetization, and this will be the same in the same direction. To magnetic field. Regarding this will be the same, attracted, but difference will come. They are strongly attracted. What happened to the first one, diamagnetic? They feebly repelled. They feebly attracted, they strongly attracted. Strongly attracted by magnets. Strongly they are attracted by magnets. And this is the same from weaker, this will be the same from weaker to stronger parts. Example, you can take it as iron, you can take Fe, you can take cobalt, you can take nickel, all these. Even some alloys are also included. Some alloys are included. Like there's an alloy whose name is alnico. I think you must have done this in your chemistry, which is made up of aluminium, nickel, and cobalt. I think so. Just look at the mechanism of it once. So these substances are included in diamagnetic substance. So first do one thing. First note down all these. The classification of material. Yes. See, in case of a non-uniform magnetic field, if it's a non-uniform magnetic field, then diamagnetic substances tend to move slowly from the stronger to weaker parts. Regarding the paramagnetic substances, they tend to move slowly from weaker to stronger parts. Similar, both have the same. Stronger, this diamagnetic has stronger to weaker, paramagnetic has weaker to stronger. This is which case? In case of non-uniform magnetic field. In case of ferromagnetic, it tends to move weaker to stronger, similar to paramagnetic. But difference arises that it tends to move quickly, rapidly, as you have written. Ferromagnetic moves rapidly. So this is the case for non-uniform magnetic field. In case of a uniform magnetic field, if you suspend a freely placed diamagnetic substance, or you can take a bar magnet also that is made up of diamagnetic substances. If you take it, then it aligns itself perpendicular to the field. In case of paramagnetic substance, it aligns itself parallel to the field. And same goes for ferromagnetic substance, it aligns itself parallel to the field. Regarding susceptibility, also there are certain points. Points include that susceptibility is small and negative for diamagnetic substance. For paramagnetic substance, it is between 1 to 0, a very small number to 0. And regarding ferromagnetic substances, the value is very high, more than 1000 something. Similarly, relative permeability is there less than 1 for diamagnetic, in between for paramagnetic, and again, in order of thousands or greater for ferromagnetic. So there are various points that you will see. That's why I was telling you. I'll send you the picture of a table is there where every point has been covered. I'll send you there that you people can learn and easily score your marks because there's not, the rest of the things are not of use. Just text me done when you have written it.